So welcome to the rigid body dynamics sessions. So this session is dedicated to force representation, and in this session we'll discuss vectors, a brief review, 2D and 3D force representation, and then few examples to get the intuition of 2D and 3D force representation. We shall briefly review vectors, their addition, subtraction, and a couple of important laws, that is associative and commutative. Vectors are quantities that have both magnitude and direction, such as velocity, force, or displacement, as we know. We represent a vector with the arrow where the length indicates the magnitude and arrowhead represents the direction. And here I have represented two vectors, a dash, b dash, and ab. Both vectors may represent same quantity because the magnitude and direction both are same. To add two vectors, we use tip to tail methods. For example, if we have vector A here and vector B, so what we can do, we can place the tail of B at the tip of A. The resultant vector is drawn from tail of A to the tip of B. This is also called a resultant vector, shown here as vector C, that is equal to vector addition A and B. The bold-faced letter represents vector. And vector subtraction is also very similar but in a reverse direction. For example, A minus B means adding A to minus B, where minus B has the same magnitude as A but points in opposite direction as shown here. So we can have vector A and then we can add minus B vector to get finally vector C, which is A minus B as shown here. Then we have associative law. Associative law states the grouping of vector that doesn't matter in addition. So if we have vector A and B and vector C, then we can have vector A plus B plus C, or we can have A plus B and then plus C, or we can have A plus B plus C. So all are same. So that is what is the meaning of associative law, that how we group the vector for addition doesn't matter, the result. In the case of commutative law, it states the order of the addition doesn't matter. So if we have vector A and B, again whether we add A plus B or we take B plus A, it will remain same. So we have A vector and B vector, the addition is C. If we take vector B first and then add it to vector A, that will also result into same vector C. So these law makes vector addition consistent and predictable for our applications in engineering mechanics and dynamics. And vectors are basically the fundamentals in mechanics. Their addition, subtraction, and the properties like the associative and commutative law helps us solve involving forces and motion. That will be taking examples and the problems later in this course. Coming to the scalar product is regarded as the product of magnitude of one vector and the scalar component of second vector along the direction of first vector. That we can see if we have vector A and B and two vectors are making angle theta between them, then we can write dot product as A dot B is equal to A B cos theta, where B cos theta is nothing but it is the projection of B along A, and that is equal to B cos theta. So whenever we are taking dot product of two vectors, or we are taking dot product of one vector to the other vector, that we can also take the magnitude of one vector and the magnitude of the projection of second vector along the first vector, and that is the important identity that we have to understand in case of scalar product. So whether we take A dot B or B dot A, it will remain same because it is a scalar quantity. The outcome of dot product is a scalar quantity. In case of vector product, it produces another vector whose magnitude is a b sine theta if we have a and b two vectors, and it will be a vector quantity. And the third vector acts along the perpendicular to the plane that contain two vectors. And for example, if we have vector A and vector B as shown here in this figure, with angle between them is theta, then the vector C, that is the cross product of A and B, is given by A B sine theta, or we can say it is the magnitude of A and magnitude of vector B, and then the sine of the angle between two. And this direction C, direction of C, is the perpendicular to the plane containing A and B, and this you can estimate from the right hand rule. If you put your fingers along this vector A and then curl your finger along vector B, then the direction of thumb will give you the direction of the third vector, that is C, that is A cross B. So if we take B cross A and then if we use right hand rule, what we have to do, we have to put our align our fingers along the direction of vector B, and then we have to bend our finger in the direction of A towards A, and then the thumb will go down, that you can try. And the direction, it means that A cross B is equal to minus B cross A because both are opposite. Representation, it can be represented in two ways. First is the rectangular component. We can have the force F. We can resolve this force F in 2x and y component. Fx is the adjacent component, that is Fx would be equal to F cos theta and Fy will be equal to the F sin theta. And for example, if we have this force F as 100 Newton and theta is 30 degree, so we can find value of Fx is equal to 100 cos 30 and value of Fy is 100 cos sin 30. So we can make use of the calculator to find it. Cos, what is the value of cos 30? So it is 0.866 multiplied by 100, so it will give you the value 86.6 Newton. So it is 86.6 Newton, and this value will be 50 Newton because sin 30 is half. So likewise you can get the values of Fx and Fy. These are the rectangular component of any force. We can also have the parallel and perpendicular component of the force. If we have some inclined plane, the inclination of this plane may be given with reference to this horizontal line or vertical line, or sometime it is given with reference to the force through the horizontal line or the vertical. So in this case, if this is theta, then this would be 90 minus theta, and this this particular angle would be, this is theta. So this angle would be theta because these are the parallel lines. This is parallel to this, and this vertical line is parallel to the force. So for this particular case, if this angle is given, then Ft is Ft would be this much, and this is F cos theta because theta is defined with reference to this line, and F normal is F sin theta. So we can also add the vector forces as simple vector addition. If we are given with two forces F1 and F2 with reference to the fx component and fy component represented by the unit vectors I and j, and similarly here f2 we can find out the resultant of these two by adding vectorically, then we get minus 20i plus 80j. We can also take some few more examples for your practice. We can represent the force in rectangular component. So certainly, as this is 30 degree, Fx is equal to 75 cos of 30 degree. We can take example f not, this is not Fx, this is Fy is 75 cos 30 because this angle is with y-axis, and Fx will be equal to 75 sin 30 degree. This is in positive direction. Here I can take projection, and this is in the negative direction. So we have to put minus sign here. So value of Fy will be 75 into cos 30, that we can write here in the calculator. 75 cos 30, it gives 64.9, may be taken as 64.95 in negative direction. So, or otherwise we can write this force F as minus 64.95 J, and Fx is 37.5 Newton. This is in positive, so we can write here 37.5 I, or rearranging this we can write 37.5 A minus 64.95 J Newton. So that is, these are the component. So the another problem is represent force in tangential and normal direction. So in this case, this is the horizontal force. Now we have to resolve this perpendicular to this. So perpendicular line is this, and the horizontal line would be this. So the component would be this one and this one. So here this is the tangential component, this is the normal component, and as this angle is 60 degree, so we can have this line is parallel to this line, and this line is parallel to this FT line. So we can have this angle also 30 degree. So if this 60 degree. So if this angle is 60 degree, then this Ft will be equal to F cos 60, and Fn is equal to F sin 60. So if this is 120 degree, so 120 cos 60, that is equal to 60 Newton, and normal force in the direction which is shown in the figure, that is equal to, it is 0.866 of this. So let us calculate this. 120 and it is sine 60, so we have sine here and 60, so it is 103.9. so this value is 103.9 Newton. So these are the normal component and tangential component as shown here. So the third problem is the resultant of the different vectors. So here it is given vector, let us say this force is F1, this force is F2, and this force is F3. So F1 we can write F1 is equal to the x component into I. So in general, f we can represent fxi, the vector, and fyj. So this is what we'll be using. So f1 is fx is nothing but 60 cos 60, and it is plus 60 sin 60, and here it is I and here it is j, and f2 we can write as if this is f2, this is the vertical component, y component, and this is the x component. So x component is in negative direction, it is minus 80, and this value is 45, so this value is also 45. So it is cos 45i plus, and this vertical component is in positive direction, so we will be having 80 sin 45j, and similarly f3, this is in this direction, so this component is this and this component is along this. So this particular component is in the negative x direction, so it will be minus 50, and x component, so fx is this value, and this value is basically, now we are given angle with this, so y component is the cos component, x component is the sine component, so we will be having sine 30 degree, and then this is again in the positive y direction, so we will be having plus 50 cos 30, this is I and this is j. Now you can compute these values and check and write the answers. So when we use the total force, then we have this component plus this component plus this component for I, and this component plus this component plus this component for j. So likewise we can add these forces. Presentation. So for this we will be taking one example straight away, because we have to find, or you make use of some basic fundamentals of vectors, position vector as well as unit vector. So in this particular example, we are given with one cuboid of dimension 3 into 4 of 12 meter height, and one force is shown from A to B as shown here. So this is B. So force is shown from A to B of 260 Newton, and one force from B to C, that is 100 Newton. So we have to find these forces in vector form. So for that we have to first find out the position vector. This is step number 1. Step number 2 is to find out the unit vector along the position vector, and third is the force vector, or the vector using position vector as well as the unit vector. So as we know, let us assume that if we have some force vector AB, and unit vector of this will be represented by small letter u with cap. So u cap AB is the unit vector of position vector AB, and the position vector AB we have to find out first, then we have to find out the magnitude of the position vector, then we have to find out the unit vector, and then multiply the force, value of force with the unit vector that is in the direction of the force will give you the value of the force, because unit vector will only show or represent the direction, the magnitude is 1. So that is what we will be using for finding the force FAB and also the force FBC. So I will be giving you the derivation or the solution for FAB. So I expect that FBC you will find on your own. So unit vector along AB, first we have to find out unit vector along AB. For that we have to find out position vector from point A to point B. That position vector, you can take position vector from any point to any point along the line of action of this vector. So but as A and B are clearly defined, so we'll be taking the position vector of AB. So we have to move from A to point B, and we will be considering the direction. So first we will move along X. So this is the movement that we have along X, that is 4 meter in negative direction. Then along Y, that is 12 meter in positive direction, and then along Z, that is 3 meter along Z axis. So that is positive. So first is negative and rest all are positive. So position vector, as we have just explained, it is -4 plus 12 along y-axis and plus 3 along z-axis. So this gives us the position vector of vector AB, and here is the magnitude. So once we know the unit vector is given by this value, and now we can find out the magnitude of this force AB, which is given as 260 Newton, multiplied by this unit vector will represent the force F, that is 260 Newton in 3D. So this is the force that FAB is representing in vector form, FAB, that is along. So let us also discuss how we can find out the force along vector BC. So this you have to do on your own. So we will first find out the position vector from B to C. So we'll be moving along x-axis 4 meter, that is positive, then along y, that is negative 12 meter, and there is no third movement, z movement for this. So k component will be 0. So this BC force will be represented by only I and j. So it is the position vector is plus 4I, and then it is minus 12j. There is no there is no third component. So this is the position vector BC. So now we know the position vector BC. We can find out the magnitude of this, then find out the unit vector, and then finally find out the force FBC, and that is no doubt 100 multiplied by this unit vector that you will calculate. So try this and get the answer. The another important aspect is the force component along another force, that is also we have discussed in dot product. So to find the component of a force along another force Q, take dot product of the first force F with the unit vector UQ of the another force, that is the second force Q. So that is what is being represented here. So this is force F, we have another force Q. So what we have to do is we have to take dot product between the unit vector of Q and the F, and as we know, the unit vector dot product of unit vector Q and F will give you the component of force F along Q, and along Q is the direction that is represented by unit vector. So that is all for this today's session. So you solve this problem and come back with the solution. Thank you.